All right, today's lesson is going to be all about something called a titration, which you probably were introduced to in honors chemistry, but you may not have done a lot with it. So let me just go over what it is, then I'm going to do this graph and we'll go over some problems as well. So a titration is a lab method where you do an acid-base reaction and it allows you to calculate the concentration of an unknown solution. So, I mean, you know the solution, but you don't know the concentration of it. So a couple of things. You need to know that it's a lab procedure and that the point is to determine a concentration right here. There's some vocab that goes along with this. The equivalence point is the point in the titration where the reaction is completed. So it means that you have run out of something. So maybe you ran out of the H plus or you ran out of the base or the multimole ratio is now the same, but it's when the reaction stops. And there's another word called the end point that you might want to jot down. I think it's down here somewhere, but the end point is the point. The end point is the point at which the indicator turns color. So ideally, these two would happen at the same time, the endpoint and the equivalence point. If you choose the indicator that turns color at the right pH, then it will turn color when the equivalence point happens. That's the whole point, is that we need to see when the reaction is happening, and most reactions you can't tell when they're finished. So the indicator will tell us that. An indicator, like it said, is a substance that undergoes a color change based on the pH, and it's going to change based on the equivalence point. And I'm going to talk about these graphs in just a minute, but let me just go ahead and explain about this process. So this big, long, tall piece of equipment is called a burette, and it's upside down. So it's read from 0 down to 100 usually, milliliters. So you're going to put some base in there, or acid, it doesn't matter which one, but in this case we're trying to figure out the concentration of the sodium hydroxide. And then in the flask at the bottom, notice there are two things. There is the concentration, or it's an acid that you know the concentration of. So we know that it's hydrochloric acid, we know the concentration, and we're going to measure out a specific amount. So we know the volume of the acid as well. Phenolphthalein, this big long word right here that looks like it has way too many vowels, is an indicator. And it's going to be clear in an acid and then bright hot pink in a base, and then it's going to be faint pink when it's neutral. So what you do is you turn this little stopcock right here until it starts to drip. And as the base drips into the acid, it's going to start to change the pH. So initially the phenolphthalein is going to be clear, but as you add the base, it will turn pink. Now, as you add base, it turns pink and then you swirl it, and as it mixes up, then it turns back clear again. But it gets harder and harder to swirl the pink away until eventually you can't swirl the pink away. And hopefully you stop at the faint pink when it's the equivalence point. These are really hard to do because one drop, I'll show you why in just a minute, but one drop beyond the equivalence point will get you into the base pH region and it'll be bright hot pink. So usually in college, you have to do several trials of these before you can get one right because it's pretty difficult to get it at that faint pink. Once you have finished the titration, so you stop the base from going down, and this has gone down some. So you started with a certain amount, and then it's going to go down. And so this is going to be your volume of base right here. And then we can use this equation to calculate the molarity that we don't know. So in that equation, 3 of the top 4 variables you're going to get from the lab. So we knew the volume of acid, so the 50 milliliters is the volume of acid. We knew the concentration of acid, so there's our molarity of the acid. We got the volume of the base right here from the burette, so that's the volume of base. We're looking for the molarity of the base. This is going to be our variable. And then the last two, so you can see you can plug all those into the equation, the last two are those lowercase n's, and those are the multimole ratio of the coefficients in the balanced reaction. So what you have to do is write out the balanced reaction between the acid and base, make sure you balance it correctly, and then the coefficients are going to be the coefficient of the acid and the coefficient of the base. In this case, they both happen to be 1. And so then you can plug everything in, you know all of those variables except for this one, and then you can calculate the molarity of the thing you don't know. So that's just kind of the general idea of a titration. Now, when you do a titration, you're going to get these really cool staircase-looking graphs. So you start with a really low pH. So this first one is a strong acid and a strong base. So notice the pH is really low. And when you end, it's a really high pH because it's a strong base. And as you add the base, it's going to start to increase, and then when you get to the equivalence point, it's the vertical tangent of this staircase graph, and then it's going to turn into a base. And what I want you to notice is that the volume, so the volume is on the x-axis, the volume between here and here is a very small amount of volume. It's a very short space, but the pH goes from like 2 up to like 12. So notice that it's a real fast change in pH, and that's again why it's difficult to get a titration to stop when you need it to, because just a little bit of volume and it shoots that graph way up. You can see over here, you can compare, this is strong acid, strong base, so weak acid, weak base, and strong acid, weak base. So a common misconception with chemistry students is they think the equivalence point means that it's a pH of 7. And it usually is close to 7 if you have a strong acid, strong base situation. But if you have a weak acid, notice that the pH starts a lot higher, and so it shifts the graph up. And we're going to do some calculations to prove why the pH is not 7 at the equivalence point when you do a weak acid, strong base titration. Same thing down at the last graph. Notice that we have a strong acid starts low, but a weak base is going to end pretty low too. So it's pretty close to 7. And so notice that the pH of the equivalence point is actually going to be less than 7. So these three right here are showing you the pH at the equivalence point. And again, we're going to do some calculations where you can actually solve that to prove what the pH is at the equivalence point. And let's go on back up here. There are lots of things that you need to be able to label about this graph. It's a really common AP multiple choice question where they give you this graph and then ask you lots of questions about the different places on the graph. So first of all, you need to know that at the initial start of the titration at letter A, the pH depends only on the concentration of the acid because you have not added any base yet. So this is the point where if they say what is the pH, it's just whatever the concentration of the acid is. Letter B, this point right here, is halfway to the equivalence point. So when you're halfway from the start to the equivalence point, the pH is equal to pKa. And this is just a really useful little hint for you. So try to keep that in mind because sometimes they'll tell you that in the question, that it's halfway to the equivalence point, and ask you about the pH, and all you have to do is take the negative log of the Ka because it's just equal to the pKa. So make sure you memorize that little trick there. Letter C is the vertical tangent, so this is the equivalence point. And at this point, the pH depends on the concentration of A minus. Once you get to D, so now we're up here in the base range, the pH depends on the excess base. And then a lot of times they ask you about when is the maximum buffering going to happen, and that's going to happen on this horizontal distance right here. So from like A to there is going to be the maximum buffering. So just make sure that you can label the different parts of that graph. And then for a strong acid, strong base titration problem, right here it kind of outlines it for you. I'm going to go through in a separate video and work an entire problem for you to show you all the different steps for that.